In this video, which is part of the numerical weather prediction series, I'll be talking about the just fully coupled global weather prediction models, what we call GWPMs. Some of the main ones I've listed here are the ECMWF, or European Center for Medium Range Weather Forecast Model, and then Global Forecast System, GFS, and then the Weather Research and Forecasting Model called WRF. This one is mainly used for regional prediction. It's kind of a simple numerical model with a lot of the more updated parameterizations and things like that, and it's best for implementing and testing the new parameterizations. What is a parameterization? I'll talk about in a little bit. Currently, between these two, which these two are models that are fully coupled, and they're meant to do weather prediction, but they have ocean model, land model, ice model, atmospheric model. It's all combined. This one is, I guess, Europe's model, and this one is America's model. But currently, ECMWF, if you look on windy.com, then they have a resolution of around 9 kilometers. GFS is 22 kilometers. While there are some differences in like how they treat land and ocean in ECMWF versus GFS, I believe the main improvement in how ECMWF is more accurate is because of this resolution difference. So that's that. So today I'll just talk about GFS because honestly, both models are hard to understand exactly how they're set up, but I'm more familiar with GFS, so I'm going to be talking about that one. Also, there's some future updates to GFS, which I think in the future could actually make it end up being more accurate than ECMWF. And I'm definitely more, I have better understanding of this. So first, we'll talk about the initial conditions. Initial conditions are what you input to the model to start integrating. So you have some current data like the temperature of the ocean, for example, or the wind speed at every location on Earth or something. If you could get that would be the initial data, and then the model runs after that. You don't need to do any more data collection once the model starts running. And then I think every time they do some data collection, you basically assimilate the data back into the model again with the current model data to kind of correct it. So like correction with measurements is also something I think that's done. I'm not exactly sure how, at what time they do that update. But the way that they do it in GFS is called GDAS, which is the Global Data Assimilation System. They use, this is kind of in their own words, they say they use maximum amounts of data. So like from satellite and also conventional data. So conventional data would be like weather balloons, buoys, aircraft ship reports, radar, model reanalysis, and land surface observations data, etc. But there are some limitations currently. I think in the future, hopefully we can get a better system, but currently we have a lot of spatial gaps, so the data is not evenly spaced. So if you have like one data point here, it won't look like this. It might be one here, and then there's one here, one here. They're not evenly spaced, and honestly, this is not too much of a problem because this data assimilation method, which I think they probably use something like 40 var, which even if the data is not evenly spaced, it can actually make it evenly spaced and find data points that don't actually exist, but use the data to do some sort of an interpolation to get that. It's also based on like statistics. So that's not big of a problem, but I think the bigger problem is sparse data regions, because sometimes in open oceans, there's like no data collection or polar regions. So you might have a bunch of data points here over land and then nothing in between, and then a bunch over here. And the data assimilation will try to come up with some points for this area based on these two areas. But that's not really accurate. If if these are all over land and the ones in the ocean they're ocean, they're not land, it's like a fundamentally different process, it won't work. So buoys are also in the ocean, so luckily it's not that bad, but there are some regions where there are no buoys, mainly because governments over there don't. There's not governments there want to spend money to do that. So improvements in satellite will help. I think buoys is fine. I think it's something they should add. But of course, there's also issues with, turbulence. So like very small resolution data that is not very uniform, the data assimilation may not be as accurate for. There's also temporal gaps, so non-continuous data sources like weather balloons are only they're not sent up constantly, they're like sent up kind of at a little bit random times. And the 4D var, it's called 4D because it's 3D plus time. There's also limited time resolution that these can get. Like they can't go down to like a millisecond. Maybe there might be some limitation. Honestly, it is something maybe will never get corrected, but I don't think it's as big of a deal. We've kind of seen that weather prediction models are pretty good at doing this, even if their time resolution isn't like super ideal. Instrument errors like sensor calibration issues and also indirect measurements. Satellites do not actually directly measure temperature like a thermometer would, or an anemometer, a thermometer. So they have to do some sort of calculation between the radiation that they see and then try to figure out what the temperature is. Also, satellites kind of see a top-down view. They can't really see within. So that's something I don't know if may never get fixed. And that's kind of definitely presents a challenge because there's probably areas where, where we can't put measurement devices. But there are some things that I think are coming up, but we have already, but are becoming improvement, called vertical sounders, which can basically give us a profile in the vertical direction of something like velocity. Those are getting better and more high resolution, and I think the way they do it is they have like a satellite, and this satellite keeps sending like pulses down, something like that, or views it from different angles and combines to get a single vertical profile. So that's an improvement that could happen. Okay, so for boundary conditions, I'm actually unsure exactly, but here's what they likely use, just based on my experience with different numerical models. If it's a global model, they're going to do periodic everywhere because Earth is approximately a sphere, and if the domain looks like this and you go out one side, you should come back on the other side. Currently GFS is I think it is like a gridded model, like square. It's not perfectly representative of a globe because these corners are going to have issues when you try to do some sort of periodic boundary conditions. At the surface, I think for air and ocean, it's probably the same, where you have semi-slip. So this means that that vertical velocity cannot go through a boundary, but it can move in the horizontal directions. It cannot move up and down. It can only move in horizontal directions. That's what free slip is. But semi-slip means I think there's some sort of friction when the air is right at the boundary. The friction between the surface is parameterized somewhere in there. I'm not 100% sure exactly how that's done. But I think for the land surface, semi-slip's pretty good. But what about like the sea surface? I'm assuming they still use semi-slip, and the effect of vertical wind stress, which honestly vertical wind stress isn't even usually looked at all. But if you wanted to, you could have a parameterization for vertical motion of air on effect of like another fluid, like the surface. And honestly, I think my hope for the far future is that they eventually get rid of, an air-sea boundary and simply have two fluids, one with density of water, one density of air, kind of touching each other, and then you can see the effect of wind on there. But I'm pretty sure right now they probably use something like this. Free slip is used at the top of the atmosphere, so there's not really any friction because the top of the atmosphere is not a real physical surface. But it does actually have some sort of probably has some sort of surface tension. I'm not sure. And then other thing is input variables and fluxes. So if there's other models in GFS, like the ocean model, land, soil, sea ice, or radiation, that's going to come in as some sort of forcing to the model. Because the reason why you think of it as a boundary condition is because they're calculated separately at in between each time step. So the model runs in between, it does that calculation and gives some boundary conditions. And they're not initial conditions because initial conditions are usually only provided once from real data. So next is here's some parameterization types. These are the main ones. I'm pretty sure there's no this is comprehensive, but I might be wrong. But one is radiation. So these atmospheric models don't have really anything to do with these radiation models, but you need them because the heating has a certain effect on the atmosphere, a very important effect. So we have radiation and in that there's things like shortwave and longwave radiation and also cloud interactions. I just summarized this as shortwave is the radiation that comes down from the sun, longwave is the one that comes out of the surface. But you can also have downward shortwave upward shortwave and downward longwave based on reflection and cloud interactions, etc. Microphysics would basically be the number of particles of water vapor, cloud, water, rain, etc., and also representing the phase transitions between, for example, water vapor, cloud, water, rain. Again, those phase transitions. Convective would be, microphysics, as from the word micro, they're very, very small. I think micro, I forgot, is something like 10 to the negative 3, 10 to the negative 6. And this parameterization is basically trying to represent these. The fact that they're called parameterizations is basically saying maybe we know the equation for this, maybe, and if we do, we can't actually resolve it. So we need to come up with a way of seeing within a bigger grid box what is the microphysics happening in between that we can't actually calculate. That would be one reason that something is called a parameterization. Another is that maybe we don't know the physical equation, but we have some empirical data. Empirical means lab derived or statistically derived from measurements. So that would be another thing that a parameterization would be. So I think this is probably a combination of those. Now, convective is supposed to represent exactly what microphysics is supposed to represent. But in this case, we're just looking at kind of the empirical data for clouds only and kind of maybe not necessarily thinking of microphysics. And so these usually have to do with shallow and deep convection, parameterizations, like a way of representing in the model. Updrafts, downdrafts, entrainment, detrainment, which is like air entering and exiting a cloud. Then for land soil, it has to do with energy balance, moisture process, plant transpiration, which is basically like plant breathing, heat transfer, surface fluxes, hydrology, which is like river and lakes and flooding and runoff, stuff like that. And also there's snow and frozen soil as well. And also I would say another one is like soil types, surface roughness, which have an effect on like the air and thus also convection. Then we have the planetary boundary layer, which again is something that the model should be able to do, but it actually can't resolve it because these processes are very small, but they also include very chaotic motions called turbulence. And I'll discuss more about PBL schemes next. And by the way, yes, parameterizations you can also call schemes sometimes. Like, for example, microphysics, one is called Morrison scheme. It just basically, because it's a way of saying parameterization. It's also a very long word, and I don't like writing it as well. Air-sea interaction would be moisture heat flux between the ocean, like from the ocean to the atmosphere, and vice versa, and then sensible latent heat flux, which is important for clouds and also heating and everything. Also kind of related to this radiation and thing, and also momentum flux, like wind stress, and also like sea surface temperature can be provided as a boundary condition. Now for GFS, based on my research updated in 2016, this is what I believe this is what is currently being used as of 2016, and there may be other ones that I haven't listed, but it is as far as I could find. So for radiation, they use rapid radiative transfer models, which are termed as RR, TMG, LW, and SW. LW is for long wave, as we discussed before, SW for short wave, and for GCMs. The RRTM stands for this, and the G specifically is because it's for global climate models, or you can think of it as just global, because I think they're used in the global ones regardless of whether it's a climate model or not. So boundary layer is called hybrid eddy diffusivity mass flux, EDMF, PBL parameterization. PBL means planetary boundary layer as before, and what does eddy mean? Eddy is kind of these turbulent motions, and turbulent means like a whirl, like these kind of like whirls like this. That would be what turbulence is. And so an eddy is the kind of an eddy is another word for whirl, and that's what turbulence is supposed to be, is a bunch of these little whirls. Diffusivity is how fast a property spreads through a medium, and eddy diffusivity mixing occurs due to chaotic fluid motion, so that's what this is trying to represent. And then mass flux is more large-scale organized structures like updrafts, which move mass vertically. And then just more explanation on turbulence. You can also think of it as chaotic fluid motion, where it ends up, the fluid starts out pretty nice, and then because of these whirls, it becomes this really hard to resolve thing. If you were to keep zooming in on this, you would find smaller and smaller whirls. It's very hard to resolve this, and so even with the physical equations, as you go smaller and smaller and smaller, you're still getting more of these over and over again, kind of infinitely, to be honest. And that's kind of the main problem with why equations like the Navier-Stokes equations are not solved, because turbulence is extremely complicated and chaotic. Okay. Another one is gravity, wave drag, and mountain blocking. I'm not exactly sure what wave drag is. I do know, so mountain blocking is usually, I think there's like a high pressure in front of a mountain, and the wind can get stuck or decelerate or something near that. This is another thing. They only occur because the models need high resolution to resolve. So I'll say to resolve. And so that's usually not possible in global weather models, because if you had a small region, like maybe I had a region that's like 200 kilometers by 500 kilometers, maybe we could do this without needing a parameterization. But for the global model, we're looking at the entire Earth. So I can just look up, for example, what is the surface area of the Earth? Just so currently the Earth is, if you were looking at the surface area, which I think is actually at the top of the atmosphere, so maybe this might be a little bit inaccurate for the surface, but if we're looking at the surface area, it's 100 and it's about 510 million km. So like if we wanted a resolution of 1 kilometer, that would be let me take a square. I mean, so in each direction, if we assume that it's that it was a square surface area, you would need well, let me make sure of something. So 1, 2, 3, 4, 5. Yeah, so I think there's like, something like 20,000 kilometers in each direction. So you would need a grid size of like 20,000 by 20,000 if you're assuming that Earth was a square, which is not, but that's just an estimate. Currently, the model that I have, it's something like 10,000. No way, not exactly. I mean, I think right now, currently, we only have like a few thousand. So numerically, it's kind of a problem. But I do think in the future this can not occur because, first of all, we're going to be including a lot of GPUs. Rather than, we're going to move from CPU to GPU, I think, which is going to, usually it's about a 37 times speed increase. And then also we can split into many, smaller like processors doing work on different parts. I think the main issue now is that we don't really have a consolidated effort to just build like a super computer only meant to work on this, and having maybe hundreds of thousands of processors working at once. I think we could actually move this scale down. But another thing is the data collection needs to match, which it doesn't really make sense to go down to a level below that. But I think currently the thing we need to strive for now is getting the current data collection to the models to end up matching what our current data collection is. So, okay. Now, for the gravity wave drag, these are the papers that are used, that are mentioned by GFS. I think one of the important ones is anything by Arakawa. The Arakawa one is pretty good. And then for mountain blocking, Loftenbauer 1997. So they basically based their parameterizations on these. I don't know if they used the exact one or if they just copied or kind of used it as a basis for their own. For convective parameterization, they say they use a new mass flux based on bulk mass flux deep convection parameterization, but they do it for shallow convection. This bulk mass flux parameterization was formulated in the 1970s. Who's the first one to do it? I don't know, and I don't think it's really written down for where I could find it. And these parameterizations formulated in the 1970s were a basis for the Arakawa-Schubert 1974, which is one of the main bulk mass flux deep convection parameterizations. And then for deep convection for GFS, they use simplified Arakawa-Schubert scheme, SAS. Scheme. As for the land surface model, they use the NOAA land surface model, or NOAA LSM. Kind of like we talked about earlier, they try to take into account all these processes, and then a lot of new stuff is trying to do it for frozen soil and snow, mountain snow, sea ice, etc. there's more information on all the citations for this, because this is a huge project that combined a lot of different parameterizations into one model. So there are like tens of, maybe even 100 citations to look at for that. And I do want to go look into this in the future, but it might be a really big project for me. I do work in atmospheric science, and I think it's not 100% my job to understand all these parameterizations, and I definitely respect that the people who work on the land surface model, they know what they're doing, and I don't necessarily need to fully understand that, and I feel comfortable applying this in a model as well. Now, current parameterizations, here's some other ones that I'm kind of aware of, and I think the ones written here are probably the best ones that the new models I believe should be replacing and just using these. An old one for convective parameterization, old one is called TKE. This one's actually pretty good still, but there's one now called new TKE, with kind of updated one. Grell-Freitas, now they have one called scale-aware Grell-Freitas, and then also new ones called Kane-Fritz. Microphysics, there's WSM6 class, Thomson scheme, Kessler scheme, and Morrison scheme. I personally like Thomson and Morrison. Planetary Boundary Layer, there's YSU and MYNN. Land surface, we already talked about NOAA, LSM. Radiation, again, we already talked about RRTM, GSW, and LW, but there's also one called CAM, SW, and LW. This is a community atmospheric model. Another thing is called a large eddy simulation, LES, which is a kind of a method that lets you resolve sub-grid scale things with a simple, easy to calculate model that's based on turbulent kinetic energy, which is also known as TKE, so turbulent kinetic energy. And this kind of, a lot of parameterizations don't need to deal with this issue of not being able to resolve the processes at a close enough scale to what they actually are in real life. And by the way, what do I mean by resolve? To resolve something, the usual, I think, consensus is that you need to be able to split a process, such as an updraft into a cloud, where it's kind of up and then there's some little, kind of goes down on the sides. This kind of updraft into the cloud, you would want to split that updraft into 4 parts. So you can, 1, 2, 3, 4, and then each part should have 4 parts. That would be the kind of best way currently to resolve it. And if you can go to 8, 16, et cetera, it's even better. But this, by allowing to represent these subgrid scale things, kind of resolve the turbulence, then it kind of removes the need to do a lot of these PBL schemes. Which the main reason we even have PBL schemes is that the resolution needs to be much smaller to represent these turbulent eddies in the planetary boundary layer. Now, upcoming developments, one is the model for prediction across scales, also known as MPAS. They basically have a new dynamical core called MPAS core, where instead of it being this kind of grid, which you actually see in the background here, this grid like this, it's made up of these pentagons, hexagons, and also I think 7-sided shapes you may find somewhere as you get into this kind of region. The reason, and this is called unstructured grid, and the reason this is better is, first of all, it has a better representation of Earth's geometry, so it fixes the pole problem, which is in numerical models when you try to fold. It's kind of like taking a piece of paper and trying to fold it. When you're at the edge of your image of the globe and you try to go out, then you should come back in. Here, go out, should come back in. When you fold this together, there's an issue at these edges here. But when you deal with this, the whole thing is connected without any weird corners. So you won't have weird numerical numerical instability at the edges. So that's why it's great. It's also really easy well, okay. It's usually really easy to define the um, like how the periodic boundary condition works. Also allows for better regional zooming, so you can actually have subgrids within. So instead of saying, well, we have this gigantic Earth, we have to resolve everything to a low level, we're like, no, just keep all this at a really easy resolution to work with, and then for your specific application, you can zoom in. And of course, the goal is to make this zooming everywhere, so we have the best everywhere. But at this current time, since we can't get that, well, we can at least make it very flexible, where we can make this region smaller, and eventually, this is small, but Africa isn't. When Africa runs their model, they could zoom in here, but not in America. But then maybe in the future, both of these can be zoomed in on the global models. And honestly, yeah, I think this is a good fix for what we're currently dealing with. We could basically say, okay, areas that we don't really need as good weather prediction because there's not really anything, maybe there's not really much stuff there. We could just say, okay, we want to go over the land masses only, and maybe we want to do the Pacific Ocean because that's important for cyclones. Maybe we want to do the Atlantic Ocean, but then other areas we don't need to focus all of our efforts on. Okay. Right. It's easier to obtain, also easier to obtain higher grid resolution without as many computational issues. I think the main reason that I'm talking about is if you have this shape, which is like this hexagon, you can have fluxes of air coming in, numerical fluxes from all sides. So you actually get a better representation of the wind flow. So it kind of gives it in a way, it gives it better resolution because it's 5-sided instead of 4 or 6-sided, for example. Okay, there's also a need for streamlining. Sorry, this is lining. Streamlining of current coupled systems for global weather prediction. This is currently all the kind of models that we have, I think, for GFS. This is a mess, and it really honestly hurts to look at. And the kind of fix for this that has been proposed and is currently being worked on is the Unified Forecast System, UFS. The idea is UFS is going to replace GFS, and maybe also WRF can be UFS too, but that's maybe not going to happen. UFS will use the MPAS core, and UFS will be a fully coupled with all known physical processes on Earth represented. I mean, there's probably some that are not, like maybe there's some exceptions, okay? Like maybe earthquakes might not be on it, but it's a possibility. It's supposed to be a system that will make it really easy to combine and couple different models. So if there's a new model that comes out that says, here, we figured out how to, here's our our earthquake model, you can just put it in. But earthquakes don't really affect the atmosphere as much, so I mean they can affect the ocean, so maybe that's an important model to add, and then they can do that. So it's also going to, I guess, hopefully include the up-to-date parameterizations and coupling between up-to-date coupling as well between atmospheric ocean, land, sea ice, snow radiation, etc. And here's kind of a list of some applications. They want to focus on local, regional, global regions, and then time spans of hour, day, week, month, year for weather. There's going to be like warning systems, hurricane analysis, marine and coastal modeling, even air quality, which is new. The national water model is going to be included. I think that's one of the most important things now that I look at it. A combination of hydrology like flooding and weather prediction is definitely something that's needed. Ocean and atmosphere are going to be coupled. There's going to be air land, so air sea. There's going to be air land. There's going to be hopefully land sea. And so I think this is like a great progress that humanity's making, and I actually hope to work with UFS in the future, especially if they're going to use the MPAS core. The plan is, compared to what this coupling is, like what the heck, look at all these arrows. This is supposed to have better organization of coupling communication between the different models and also between the processors. As for a little explanation of what is coupling communication, what does that mean? Well, some of these models are ran at different resolutions that are needed. Like maybe a land model needs a specific resolution, a lower resolution than an atmospheric model to actually resolve these processes. So they come in at different resolutions, and the model needs to use something like data assimilation through what we talked about, 4D VAR, for example, to put the resolutions on a common resolution scale for everything once they've already been calculated at their resolution. And that's better. That it's not like moving it from a lower resolution to a higher resolution will actually mess it up as if we had ran it at a lower resolution on a numerical model in the first place. What we do is we run maybe the land one at a higher resolution, and then when we combine it, where the atmosphere one is lower than that, so we want to put it on the lower scale. The values that you put in are actually still just as accurate, almost just as accurate. And it also I believe it should allow for flexibility for regional modelers, such as customizable resolution settings. So if I want to run it at a different resolution, I can interpolate it to that resolution, interpolate the input data to that resolution, and then I can keep running it. And that's what I was talking about earlier. Maybe WRF can be replaced by UFS. And then we won't have too many different models, and we can keep everything kind of consistent. However, one argument against that is that, well, if we keep everything consistent, maybe there's a better way, and we don't look for it. So I think what they should do is allow like a full list. I think they should have like a full list of all the possible parameterizations, all the possible models, and just say if you're a researcher, you can pick and choose which ones. That would be, I think, the ideal one for me. But honestly, I think that's maybe a future advancement that's not going to be made at first. I think in order to have all the models on there, it requires a lot of different code. But I think a better way of doing this is to include and make it so the coupler can simply run another model, so the researcher can set up another model, and you can connect them so you can run the model using terminal commands or something, and then they can just use that as boundary conditions without actually needing to make the code for UFS the same as the code for that other model that's not used before. So instead of making a list of all of the possible ones, because there's a lot, just say, well, you can use any one you want, and we'll connect it for you. So I guess I could say like connection. Maybe how do I say it? Maybe I can say coupling connection for outside models. Okay. And I already mentioned before, which I forgot to write here, is switch from CPUs to GPUs. So GPUs, as you know, are the ones that are used a lot for video games, and if you've seen like any of the modern video games, or something like Minecraft, like anything where you see all these visuals and they have to be rendered. So you can have video games that rendered entire environment, it looks super HD. GPUs are made to be better for these kinds of processes that a lot of numerical models are doing calculations for. The calculations in video games are mapping a location, an object is like a chair, each part of that object to a specific location in the game that the video game camera can then see. So GPUs are much, much better at doing this kind of image processing, which is basically what numerical models in a way are. And instead of CPUs, I guess the main thing about GPUs is that it's kind of seen as like it's kind of in the same format as numerical grids too. It's kind of like this grid style kind of thing, and you can easily, well, maybe in some ways complicated, but sometimes easily split these into different parts and have them run on top of each other, and then have all the other ones run separately and then have interaction. So it's kind of a easier way to do multiple processors. So multiple processing. So I would say one, it's better for how do we say that, like multiple, I think there's a better way of saying this. I'll say multiple processing, and then it's better for image processing, which numerical I would say instead of for imaging processing, it's kind of for calculations, or better for fast and many calculations associated with image processing, which could also be useful, or not could also, which is also useful for numerical calculations. So that's another thing. I'm sure there's some other reasons that it's better to use that I maybe haven't mentioned or haven't written down, but these are kind of the main two important ones. So that will be all for fully coupled global numerical weather prediction systems. And the next thing I'm going to look at and try to go into, but I actually need to learn, something I've looked at a little bit before but want to get more, I want to complete my understanding of, is 4D VAR, which I discussed in this, which is a data assimilation method. I think it's like the best and most modern one. So that's that. So yeah, stay tuned for more videos, and like and subscribe if you want. Yeah, thank you.